before that, before connect, can you send me the presentation file to me as we did?
Yeah, sure.
If connect, then everybody will see
Yeah, right.
your password.
Yes. Yeah, so let me. Okay. Gmail is Gmail. Oh, text. Clemson too. You put Clemson there. Clemson. Yeah, Clemson 2. You can also send Clemson 3. The 4 I need to make some changes. But 2 is the one I'm doing now.
2 and 3.
Yeah, so 2 is the one that has the 1 is the latest one. No, this one.
2 and 3. Oh, this is huge.
Huh?
Really big file.
Yeah.
Your presentation. Yes.
Oh, that's good. Okay, any questions before we start? Okay, so as I said yesterday, the key for inverse problems, or not all, but many inverse problems, is to find solutions of the equation as explicit as you can. Right? So because of for instance, in this case, this is a function of x. It's not so easy to solve explicitly. Actually, we don't know explicit solutions. But what we're going to try to do is find what are the singularities of the solution. So we start with the plane wave in the past. So this is the support of Q is contained in this ball of radius r. Then you send a plane wave coming in with direction omega. So this moves and then interacts with the potential. You want to see what comes out in the other side, right? And see what information will give you about the potential. So the plane wave is modeled as a delta function here. So that means integration of the function along the plane. X, this is the plane x dot omega equal to t. And so the first problem is to show that this will be one exercise for that this solves the wave equation. It's a wave for this is the usual inversion. And so we try this at the first ansatz. So it doesn't work because when you apply this to this, the wave equation applied to this is 0, but then you get the term q times that. So you want to get rid of that. So for that, you consider what you had before, plus an amplitude here to be determined times the Heaviside function. Of course, this is an ansatz, meaning it's an idea, right? So the reason for the Heaviside function is because when you differentiate the Heaviside function, it gives you the delta function. Yes? Sorry? No, in any dimension. This works in any dimension. So the wave equation you also can check that the wave equation of the Heaviside function, this is also a plane wave. So plane wave, the difference is that this plane wave is 1 here. This is t equal to x omega and 0 here. That's why it's called progressive, although it's the opposite of politics. Progressive moves to the right. So, and then the wave equation also is 0, so that's another exercise. And then when you try the new ansatz, so this is the U1. You try this one. We don't know A1. We want to determine the amplitude of this wave. And then you do the computation, and this is what you get. This comes from the differentiation of the Heaviside function. But still, you will get a term involving the Heaviside functions. But this involves the delta function, and we want to get rid of this term. And so we choose A1 so that the gradient of A1 dot omega is equal to minus the potential over 2, so that we kill this part. We shouldn't say kill, but we eliminate this part, right? So this is the way we choose. And we want A1 to be 0 in the past. A1 to be 0 when x dot omega is less than minus r, so that we get the plane wave that we want in the past. And then this is the solution. We integrate. This is a directional derivative of A1 in the direction omega. It's a very simple ODE. And then the solution is simply the integral of the potential along this line. So you have a line here with direction omega. And to get the solution here, we just integrate minus the potential over 2 along this line up to here. This is just a simple ODE along the line. But if x dot omega is sufficiently large, we're going to go out here, and we're going to get the integral of the potential over 2 minus the potential over 2 along this line. This is the X-ray transform that we talked about yesterday, and Ruyu considered this morning. So we're going to recover the X-ray transform of the potential. Yes? So the main singularity here is the delta function, right? On the right-hand side. We want to get this equal to 0, but but we're not going to be able to do. Every step, we're going to get something better and better in terms of singularities. So we eliminate this singularity, but we still will have this one. Okay, so we eliminate this first, and then we get the A1 is equal to to compute it at any point, you get the integral from the past to here. But if you go x dot omega is sufficiently large, bigger than r, in fact, this is the Borel radius r, then you're going to be out and you're going to get the integral of the potential. And that's the X-ray transform which appears in X-ray tomography and CT scans. This is a connection between wave equation and tomography. So if X, this is what I said here, if X dot omega is bigger than R, this is the X-ray transform of minus X over 2. So this, the X-ray transform, remember, is the integration of a function along the line with direction omega. Okay, so but this is better. You get 0 here, so, but you still get this term. So we need to eliminate that term. How do you eliminate this term? You use another amplitude times t minus omega plus. So t minus omega plus is equal to 1. Sorry, is equal to not 1. T minus x omega, if this is positive, and 0 otherwise. So this is s plus to the k is sk, so this is plus corresponds to. So the reason for this is because you take the derivative of t minus x omega plus, derivatives of this gives you the Heaviside function, right? In terms of singularities, when you differentiate plus is like this. Is like this. So this is 0 here, and it's s here, or t minus x omega. So you differentiate this, you get 1, 0. You get exactly the Heaviside function. So we try that, and then we need to solve this equation. I mean, and this is just, again, the integral of this function now. We know already A1. We know, and then so it's the integral of this function. But this doesn't give you any new information. So we can continue this way. There is a typo here. It should be delta of t minus. Sorry, there is a delta, an extra delta here. Okay, and then we try to eliminate that. How would you eliminate that? Anybody has suggestion? It's here. You consider t minus x omega plus square, because the derivative of that is the Heaviside function. Sorry, it's t minus x omega plus, and then you keep going. And then this is getting s plus square is like this. This is s squared and 0 here. So this is s plus, this is s plus square. So see, it's getting better, smoother. This is continuous but not differentiable. This one is differentiable. And it's getting better and better and better until you can get Cn minus 2. It means n minus 2 the capital derivatives. And I'm not going to do this part. This is, you go all the way. You can sum this to order infinity, and you get a smooth error. Because this is getting smoother and smoother. This is Borel's lemma, which I don't have time to explain, but you can sum this to order infinity. But the main point from the inverse problem point of view is this term, A1. Because A1 for x dot omega, so after the wave has gone through the potential, in terms of singularities, is the same. This, well, the singularity of this, the singularities are all smooth, if Q is smooth. The singularity is here, is still in t equal to x dot omega. So there is a lot of stuff here, but we ignore it. We just look at the singularity, and the singularity is in the plane wave. So this went straight through, and the singularity does not change. However, the amplitude of the first singularity, that's the important thing, the highest order singularity, this is what you see first. Of course, you subtract this plane wave from the pass. The first singularity will be the Heaviside function, and then you can recover, from the amplitude, you can recover the potential, because we know that we can solve the inverse problem. This is the X-ray transform. Given the X-ray transform, you can recover it, you can recover the function, and you know this information. This is what Radon proved, essentially, that I mentioned before, and Ruyu also mentioned this. Okay. Okay. So this is called the progressive wave expansion. Was actually done by Courant and Lax in the 40s or 50s or early 50s. Okay, so this is the progressive wave expansion. There is another way to represent this progressive wave expansion, which is you take the Fourier transform of this. So you get e to the I t minus dot omega rho. The Fourier transform of the delta function is 1, but you get the t minus x dot omega rho. And then I will cut it up near 0. And then you get 1 from the Heaviside function, and then you get the smoother the distribution, the more decay you have of the Fourier transform, right? The Fourier transform of the Heaviside function is essentially 1 for large C. And S plus is 1 over C. This is again for C bigger or equal to 1, so it's getting better and better, and plus a smooth term. So you can represent it as an oscillatory integral here. Okay, so the amplitude is given here, and this is called the principal symbol of this U minus delta omega. So from the principal symbol, called the principal symbol because this is the first decay. This corresponds to the delta function. So this is, you subtract that. And the first term, the least decaying term, this is what you are going to observe first, is this amplitude. It's called the principal symbol of this oscillatory integral. And the other terms won't matter because the decay of higher order. So from the principal symbol of the difference of the solution minus the delta function, so the smooth error doesn't matter because the Fourier transform of a smooth function with compact support, for instance, we're cutting it up, is rapidly decaying. And so the principal symbol of this oscillatory integral determines the X-ray transform of Q and therefore Q. There is important to write this way because I will consider more general expansions, as you will see later. So any questions about this? Okay. So this is an exercise, compute the Fourier transform of these distributions for the discussion. Any volunteers? Think about this if anyone would like to volunteer. Huh? The Fourier transform of the Heaviside function. Yes. Oh, sorry. Sorry, thank you. This is what it says here, right? Here, see, this is the Heaviside function. This is the coefficient of the Heaviside. It's 1 over rho is modulus of C. And the other terms are higher order. The delta function is 1, the Heaviside function is 1 over C. So the behavior at infinity, this is the important thing. It's not exactly that. Okay, so this is the situation. So you have the support of Q. This is the plane wave, and then you get the integral of the potential along this line with direction omega. Right? That's the summary of the situation. You wait enough time that you get out of the support, and then you can recover Q. This is a very nice connection between the wave equation and the X-ray transform. And this can be generalized quite a lot, as we are going to see this picture. Any questions? So you can solve the wave equation plus potential in terms of singularities. And this is a field called macrolocal analysis, which tries to recover the singularities of solutions of PDEs. We cannot solve PDEs exactly, but in many situations we can determine the singularities, how singularities propagate. This is, you start with singularity. Here there is something happening. The support is not this. The support can be, we don't know exactly what the support is, but we know where the singularity is, right? That's the point of this. Any questions?
And we still assume the Q is L infinity?
No. For this, we're assuming Q is smooth, because we're looking at singularities. There is, if you assume less, depends on the order of smoothness. You still can do this depending on the number of derivatives that you have. But I wanted to explain the idea in the simplest case. Yeah, Q is smooth for this picture, because we went all the way. Okay, so this is the X-ray transform. I've already explained this before. And there is a nice formula that for the inversion formula. This is called the transpose, or the adjoint in applied mathematics. This is called the back projection, because you go back. You have T corresponds to the points x and omega when x is in the perpendicular to omega. So you take C infinity of, these are the lines. You can parameterize the lines this way. Remember omega, and this is the perpendicular. You have the plane perpendicular. You have a smooth function there. You can define the back projection by the following. It's very geometric. You take a point, x, and then you can, so you have a function g depending on s, let's call it s omega. And then you consider all the lines going through the point x, which are parameterized by the angle. This is the direction of the line. There are many lines going through the point x, an infinite number, right? And then the transpose, you can check that this is the transpose. This is another exercise of x, is the integration of the function along this line. Every line, this is x dot omega, represents the line, every line here, and then you vary the line. You vary omega. This is you can check that this is actually the transpose of the operator. And then a computation exercise is that I star I, which is called the normal operator. This is used a lot in matrices, right? You consider, you have a matrix, you consider the adjoint of the matrix, and A star A is the eigenvalues of this is what's called the singular values of the matrix A. That's very important. And this is a better operator in general because it's positive. Let me do this. What is the line? You drew the line very well, but let me. No, it's not there. It's a little bit here, no? No? How do you know where the line is? Okay, let me just put it there. So in general, this operator is positive because if you take this, the inner product of this in the L2 sense, you get IF. And then this goes here, because this is the adjoint, this goes IF, which is bigger or equal than 0. Is the norm of IF squared. So this is self-adjoint, and also is also self-adjoint because the star, the adjoint of this is I star and I star star, which is I. Right? The star of the star is the same operator. So this is always very useful to when you don't know what to do with the transforms. In general, this we can solve explicitly, but there are other transforms you integrate over curves, for instance. And so we don't know how to invert that explicitly. However, you can always look at I star I and see what kind of operator you get and try to invert that. If you invert that operator, you invert I. And this is the singular integral that is a singular integral. That's why Radon took the principal value, because this has singularities when x is equal to y. And is inverted by the square root of the Laplacian. So this is I star I is in fact a negative power of the square root, so it's inverted by the square root of the Laplacian. And this is called a pseudo-differential operator or a singular integral. And this is order -1 because the Laplacian is order 2, so this is order -1. So we have an explicit inverse, minus Laplacian 1/2 I star IF is equal to F. So this is the operator that Lee was considering just a fractional. We consider these fractional Laplacians, right? It's non-local operator. Okay. This is, I'm going to jump. So I'll go now to the acoustic case, the acoustic wave equation. This is going to be, we're going to consider, in particular, Young is going to consider a nonlinear version of this. So this is the acoustic wave equation. C is the sound speed, right? So it's assumed to be positive, and let's assume it's 1. This is homogeneous. It's just the wave equation for x sufficiently large. So this describes propagation of sound, use the pressure. So again, we try to solve the same problem as before. This is the unique continuation problem. So you have a plane wave. It's exercise, if you try the same plane wave, it's not going to work. So the ansatz here is different. You take an amplitude here, so we're trying to solve the same problem, but with the wave speed here. And U is a plane wave in the far plus. So this is the acoustic wave equation. Describe propagation of sound. C is the sound speed. The speed of sound is different in different mediums, right? Okay, so I'm going to consider try to get a progressive wave expansion, but the ansatz will be different. So exercise delta t minus x omega as the main term plus lower term does not work. So in this case, you will have the support of the sound speed is here, and the support of the sound speed is one here outside, so you have the same plane waves you had before outside the support of C. It's going to go through, but now we're going to see it's not going to be a plane wave like we had before because of the sound speed. So there will be a distorted plane wave, but we have to determine which one is it. Okay, so this will be called a distorted. We're going to use this type of plane waves for the nonlinear problems tomorrow. So it's not going to be a delta function, the solution. We're not going to write it as delta t minus x omega because that doesn't work. You can easily check. And we're going to consider delta, but of t minus phi x omega. So this will be t. So it starts with the plane wave, but then it will be some other function of x omega. It's not going to be a straight plane wave, but it's distorted plane wave. And we'll have an amplitude as well. Also, you can, another exercise, A0 equal to 1 does not work. Okay, this is an ansatz. So exercise, this one, let me write it here. Of course, you have to do the computation with that. So delta t minus phi of x omega with A0 equal to 1, so that means A0 equal to 1 does not work either. So you try this is it's an ansatz again. You try an amplitude here times this wave. And then plus, again, smoother terms, the Heaviside function, some amplitudes of the same thing here, but this is distorted plane wave. It's not a straight plane wave, right? Questions? And this is, so the higher order singularity exercise is when you differentiate 2 times this, because these are derivatives, involves derivatives of order 2, right? So we need to kill those. So what is the coefficients of the second derivative? So when I differentiate with respect to time, I get, this is the second derivative, I get 1, right? Then when I differentiate with respect to x, I get the first derivative of x, of phi. But I differentiate again that. So I get the gradient of phi squared. So this is the coefficient I get, it's an exercise. The coefficient of the second, this is just differentiation. The coefficient of the delta double prime, which is the highest order singularity. Remember, the idea is to get rid of the highest order singularity at every step. Is this 1 minus c squared. So we need to solve, we need to kill this, eliminate this, right? Like we were doing before. So we need to solve this equation. The modulo of the gradient of phi squared is 1 over c squared. And we want phi in the past to be the plane wave. This is this, because that's the problem we want to solve. It's a straight plane wave. This is delta t minus x omega. It's a straight plane wave in the past, right? So this is called the Uhlmann equation. I never have understood why it's a Greek word apparently, but why it's called Uhlmann? Anybody knows? But I don't know. You're Greek? No. So this is the question. But however you think, seems to be even more complicated because it's nonlinear equation, right? It's first order, but it's nonlinear. In general, to solve nonlinear equations is harder than linear equations. And we're trying to solve a linear equation. And we got a nonlinear equation. The point is that this equation is actually not so hard to solve. There is a method, it's a geometric method actually, developed by Hamilton and Jacobi to solve first order nonlinear equations. I will explain this. So this equation can be solved. And it's a very nice, actually, geometric way to solve this equation. Although it's nonlinear, but it's first order, that's the point. And the next singularity is delta prime. So the highest order singularity was delta double prime, the second derivative of the delta function. The next singularity is delta prime. And what is this is exercise called the transport equation. And you get this. 2c times the gradient of phi dot. This is a vector, the gradient of a0 minus c squared of x, Laplacian phi times a0 is 0, and a0 is 1 in the past, because we want a delta function in the past. We want the plane wave in the past. This is called a transport equation. This is what Ruyu was considering this morning, the transport equation for. But it's not along straight lines, as we're going to see. Before, in order to determine the transport equation in our case before was the integration along the line. This will be integration along other curves. It will be geodesics or some metric, but I will explain this in a minute. But this is a first order linear equation. And first order linear equations are very easy to solve. You reduce it to an ODE along certain curves. So I'm going to explain how to solve this and the conal equation, but this is much easier to solve. It's linear, you see, it involves only derivatives of a0. It's like a vector field, right? In the case that phi is equal to x dot omega, this is simply omega dot the gradient of a0. That's the equation we had before. And now it's more complicated, but still we can solve this transport equation. So it's linear PDE. So let's go to I'm going to explain the Hamilton-Jacobi theory to solve this equation. So this is the conal equation. So as I said, this is the Hamilton-Jacobi theory to solve nonlinear first order PDEs. It's more general than just this. I'm going to apply it to this. There is something called the Hamiltonian. So you go to phase space. This is an idea of Hamilton. So this is the question that we want to solve. The support of the sound speed is contained in the bolus radius r. So this is sort of precursor has been called macrolocal analysis. It was called macrolocal analysis. So this is go to phase space. It's a very useful idea. In physical terms, you go to position and momentum. But in more, I want to look at position and directions, so which is the same. So x, c. So X is in Rn, and C is in Rn, and I'm going to take a direction which is not zero. So you go to, this is called phase space. It's the same, it's completely the same as position and momentum. In classical mechanics. And there you consider something called the Hamiltonian associated to this equation, which is this one. But as I said before, you can consider much more general Hamiltonians, and there is a lot of the theory of Hamiltonian systems. This is just a simple example. So you normalize it so that this is 0 when this is 1, so that means modulus c squared is 1 over c squared. That's just because this is correspond to c squared equal to 1 over c squared. It's just a normalization. And the idea to solve this equation is to have the c as this is, because we want to solve this equation, you want the c to be the gradient of phi for some phi, right? Sorry. Because if c is the gradient of phi, then you're solving this, right? Huh? Equal to 0. You want h equal to 0. If c is equal to the gradient of phi and this is 0, then you get the solution of this equation, right? So you want to, that's why I'm saying you consider this normalization. So when h is equal to 0, you get the equation. So, but how do we get the c to be the gradient of phi for some phi, right? Is that clear? That's what we want to do. So this is the Hamiltonian. This is the Hamiltonian. And then there is some curve. Then we are going to phase space. Remember, we are going to n-dimensional space. Is the fact that when you look upstairs, everything looks much better, right? And you don't see all the problems that are down. So there are curves called the Hamiltonian, they call by characteristics. So you consider what's called the Hamiltonian vector field. So this is the Hamiltonian, let me write it here, the Hamiltonian. This is very general, it's h of xc. The 1/2 is just so that when you take derivatives, you don't get the 2. And then the Hamiltonian vector field. Depending on the C, let me call it VC. Sorry, let me use. Is the derivatives of this with respect to C in the x variable and minus the derivative of HC with respect to x in the C variable. So this is the x variables and this is the C variables. So there is a reason for this, which I will explain briefly later. This is called the Hamiltonian vector field, this VC. And you look at the integral curves when you have a vector field. This is in phase space. You have a vector field at every point, you have a vector, right? Then you consider the integral curves of this vector field, right? Which these are tangent to this. So these are called bicharacteristics. And this exercise number, I don't know what. These curves are tangent to HC equal to 0. So you start in the level set HC equal to 0, you stay there. It's very easy to check. This is for the discussion. Because remember, we want to stay on where the Hamiltonian is equal to 0, right? So you consider the integral curve, you start with a point so that you are in the 0 of HC. So this is the points where HC is equal to 0. It's called the n-1 dimensional sphere related to the sound speed. This is when C squared is equal to 1 over C squared. C is 1 is exactly the sphere. Okay, and geodesics, the geodesics, any questions? For associated to the sound speed are the projections of these are called null by characteristics. Null are, so you project the null by characteristics in X space, those are called geodesics. Of what? The geodesics of this metric. For the people who know some geometry, there is a metric here associated, which is this metric. This is the standard Euclidean metric. So the metric means you can measure lengths and would multiply times a factor related to the sound speed. This is the length in the new. So you multiply the standard metric, the way you measure lengths for the Euclidean space, just you can measure lengths of this. It's very simple, but here we have curves, and then this is a way to measure the lengths. So the geodesic minimize lengths. So this is the ds over c that we have before. So the geodesic minimize lengths, which corresponds to the time locally. So you have a curve. You define the lengths associated to this, and then the lengths. The geodesics minimize is the curve that minimizes the length. You can go from point A to point B in many ways, right? You have many curves. I will tell you how to find the length of this curve. But the geodesics are the ones that minimize the length, at least locally. And the geodesics so this depends on the sound speed, will avoid regions of small sound speed. This is called a slow. We'll discuss this point a lot. So they try to go around these speeds of sound speeds which are small. But anyway, geodesics minimize length, so you can think about that, and I will give more details in a moment. Okay, so we have time? Yeah, I have time, right? Okay, so as I said, this is going to be a little bit complicated for people who are not familiar with geometry. So since C is not 1, we are going to have the integral curves of this Hamiltonian, again, they're geodesics, and they are in X space. Okay, we're going to go to phase space in a moment. So I will go to, so this is when we start a straight line. Geodesics are, if you take geodesics for this metric, the geodesics are just straight lines. The lengths, to minimize the lengths from point A to B is a straight line, right? You don't go with this, just takes much more length, right? So how to solve the conal equation? So you start with a point x0 omega 0, so that omega this it is in this line, like here. And then you flow out, so it's a straight line, the geodesical straight line, because C is 1 here, right? And then the sound speed will be different, so the geodesics will be some curves, not lines anymore. So what you do is called the flow out. So remember from the about this Hamiltonian vector field, we have the bicharacteristics. So you flow out, means you take the curves, you start with a point. This is now in phase space. And you flow out by these integral curves of the Hamiltonian vector field in phase space. You are in phase space. Remember, we want to show that the C is the gradient of some function phi. Yeah, this is a reference for how to solve this in more detail. So you flow out, it's called geodesic flow in geometric terms. You flow out from here by the integral curves of the Hamiltonian vector field. And this is something called a Lagrangian submanifold. This is upstairs. I will explain. And then the point is that Lagrangian submanifolds are locally given. There is a phase function so that the C direction, the direction is given by the gradient of some function. It's a theorem about Lagrangian manifolds. I will explain more about Lagrangian manifolds. That is given by the gradient of some, locally by the gradient of some function. So this is the way to find Lagrangian manifold. That's the reason why you go to phase space. Yes? It has to be what? Yeah, right. Yeah, this is exactly why this is of this form. That's the way you find the phase function. Right, exactly. We're going to say this in a minute. Questions? I know that this is maybe complicated for people who are not familiar, but it's just it's a special when you flow out. You flow out means you take the integral curves starting at that point. I mean, you go like this. Of course, this is in phase space. I cannot draw it because even in 2 dimensions, it's 4-dimensional. So you start with straight lines, something happens here, and then you do this. You take all directions, right? Flow out means in X and C, so that will give you some manifold. Okay, so this is a description of, I apologize if this is not familiar, but I don't know an easier way to explain Lagrangian manifolds. So Lagrangian manifolds are n-dimensional. So we are in 2 n-dimensional space. So it's half of the dimension, such that there is a form here associated to this. It's called the symplectic form, which is given by the wedge between the C and the X variable. So if this form vanishes on lambda, that's a Lagrangian manifold. That's it. That's all what there is. So there is a symplectic form given by this. So what does it mean vanish? So that when you take this is some manifold. You take the tangent space of the manifold. So the tangents to this Lagrangian submanifold. You have some submanifold here. And you take the tangent vectors to the submanifold. This is lambda. And then this vanishes means that when you apply this form to tangent vectors is 0. That's the the symplectic form. And so that's why you are going to be able to show that this Lagrangian manifold is this form for some phi. So this is contained in Hc is equal to 0 because this is you start as I remember, if this is 0, the bicharacteristic curves stay there. Stay in Hc is equal to 0. Therefore, this Lagrangian manifold is contained here. See this. Remember, we want to check to solve the conal equation, this has to be 0. So this Lagrangian manifold, you can show that every Lagrangian manifold that is of n dimensions, this has n dimensions because it depends only on x. Right? It can be written in this form. This is exercise that Chaim will solve because he already gave the solution. It's Poincaré's lemma. And so this means that you have solved the conal equation. So this is very geometric way to solve this conal equation. I'm sure that if you have not seen this, it's maybe a little bit complicated, but believe me, there is a way to solve, very nice geometric way, but this is only locally. It's not a global solution. This Lagrangian manifold may be very complicated. If in globally, but locally it's nice, and you can write it as a graph of this function, some function phi. It's only locally, because Poincaré lemma, as Chaim is going to explain, is only local. So think about this. Okay, so this is what, it has only local solutions, because unfortunately, you can have something called caustics or conjugate points, so it's also called conjugate points. These are a nice example constructed by François Bonnard. So on the left, you don't have any caustics. Caustic means that the geodesics come together. There is not a unique geodesic going through a point. There are many geodesics, like in the sphere. We know that in the sphere, the Earth, you have the south pole up. I come from the southern hemisphere, so I put the south pole up. At least there is one person from the southern hemisphere here. Who else? Anybody else? Everybody's from the northern hemisphere. We're in a minority. There are many geodesics going through the south pole, right? An infinite number of geodesics, in fact. The geodesics are the big circles that planes try to follow the geodesic. They try to minimize lengths, try to go in the minimum amount of time possible. But here, the geodesics, see, this is an example where geodesics come together. And here, this example, they come together at the boundary of this. They're starting all at this point here. This is very nice. No bad behavior of the geodesic. There is a unique geodesic globally joining 2 points. Here, they come together at the boundary, and here is even worse. The geodesics come together inside. So there are no solutions globally because you need to have a unique solution of the equations. So this is an equation you can only solve it locally. So the conal equation can only be solved locally, not globally. Okay.
So if the caustic happen, does it induce more singularity when exiting? In the sense, inverse problem we have.
Yes. Yeah.
Caustic happen here, the more singularity.
Yeah, more singular, right. Right. And there is the theory of Fourier integral operators was developed to actually deal with the problem of caustics. Even if you have this situation in the base, here in the South Pole is very complicated. Many geodesics come there, but if you take a direction, through a point and a direction that is a unique geodesic. So that's the thing that you have to do. So that's why microlocal analysis is useful for dealing with caustics, because through every point, this is an important fact, through every point in phase space, there exists a unique geodesic passing through X in the direction C. And that's the key why going to phase space is useful. So it's true that we have caustic, this Lagrangian manifold, the flow out can be very complicated. For instance, you can have a fault. It's called a fault. So, well, so through every, there may be two, it's not a graph of some function, you can have singularities. Can be very complicated, but however, through every point and every direction, there is one geodesic. Okay. So, yeah, well, maybe I should finish here. I will continue tomorrow. Any questions before? Is that time? Is time? Yeah, because 2 minutes. Okay. Any questions before we break? I also need to talk about the transport equation. The transport equation is easier, it's a linear equation. This is, the Conal equation is a very nice geometric way to solve it. And also the transport equation. Yes.
So the starting wave equation, the wave speed was in outside Laplacian,
Right.
If you bring different under divergence, that doesn't change anything, right?
Yeah, right. Doesn't change anything. This is much more general. For instance, you can consider, I did it for the sound speed. You can consider an isotropic sound speed. You can consider, for instance, this. This is, doesn't change anything. That will be the geodesics of a different metric. The metric in that case.
That means the first order term
yeah. This is the first order term dominates everything, right? For this type of wave equations. Yeah. So the metric in this case is it was called a Riemannian metric. And then you can define geodesics. Everything here is the same. I put the sound speed because that's the simplest case. I see isotropic sound speed. Any other question? I understand that people who are not familiar with this may be a little complicated, but I believe that you can solve it. This equation using geometric. It's worthwhile studying, actually. Hamilton-Jacobi is a very powerful theory to solve. In classical mechanics, in physics, is all analysis on phase space, the position and momentum. So quantum mechanics is, then we look at the operators themselves, right?
We're going to have a short break, and we'll come back for let's come back at 3:20. So we can all clear out the building before 4:30.
Apparently, iconal is some Greek version of sorry, some German version of a Greek word meaning likeness or image. I
What?
guess likeness or image. I guess
Oh, I
so. I
see.
guess that's why it's called that.
Oh, so what it will be? Sorry, I didn't.
It's like it's a German version of a Greek word
I see.
meaning image.
Image. Oh, image. Oh, okay.
At least according to Google.
Okay, thank you for the, thank you.
Yeah, that does make sense. That's weird that you went.
Okay, so you had to do some exercise. You.
Who is behind?
You and you, you and you, you and you.
What?
You do, so he was going to do the Lagrangian manifold. And
Yeah, so can we have to do that? I mean, he has to do the rest. Sounds good to me. No, you have to.
don't be afraid. What are you afraid of?